Okay, let's start the lecture. So the following 3 lectures would be about water pollution, 2 lectures about water pollution, and then the other one about water quality control. So the actual engineering part of this course. Okay, why are we talking about water pollution or water quality? It's because it's very important to have safe drinking water. We know that contaminated water or dirty water, they cause diseases. So there are different kinds. I'm not going into details of this. Okay. And diarrhea is actually causing 4% of all deaths. So it's not, it's very, you would take it for granted to have safe drinking water in Hong Kong, but in a lot of different parts of the world is not the case, right? Mostly children in developing countries. Okay, so before we talk about the water resources, we need to talk about the hydrological cycle. So there's a lot of water in the Earth system, whether it's in the ocean or it will go to the sky or the atmosphere by evaporation, and then we'll get that with precipitation, right? So, and also we will get the water from the river, so the surface water here, the runoff. So there are different storage in the Earth system that we can get the water. Okay, but sadly, the usable water is very, very small. It accounts for 0.0072% of all water in the world. Okay, so you think that, okay, we have an ocean of water. How come we only can use less than 1% of it? So 96.5 is salty water, right, in the ocean, and only 2.5 is fresh water. Okay, and among this 2.5, if we boil this up, around 70% is stored in the ice form, which means that we cannot use it. Okay, and 30% would be groundwater. A lot of different countries, they use groundwater instead of river water. So this is a very important part of the fresh water. And also, this is the part where Hong Kong people use, right? Fresh water from the river, from the surface, or lake water, okay? And then if we blow this up, just the fresh water here, this part, we know that 70% is not the same as glaciers and ice caps. It's stored in the soil, okay? Inside the soil, we have ice. 70% of that would be inside the soil. It's called permafrost, okay? And only 21% from the lakes, and the others from the rivers, soil moisture, and also in the atmosphere. So very, very small amount. So if we calculate that from the total amount of water, only less than 1% or less than 0.01% that we can use. Okay, that's why it's very important to talk about water resources. Okay, so you think that, okay, if you open the tap, the water is here, right? But it's not the case, because we have more and more people in the world. Per capita of water per person of water, the access of water would be less and less. So per person, you can access less and less water. So this is showing you the decreasing trend. Because there are more people and limited resources for water, right? So implying that we have an increasing population, which means that for our world, it's still increasing. It's increasing in a slower percentage, right? We talked about this for the human population part, right? The growth and decay lecture, we talk about that. Still, it's increasing. So that's why it's very important to talk about this. Also, if you talk about the water resources, we need to talk about different usages in a society. Okay, so how do we understand the usage of water resources? So first of all, we withdraw or take the water from different parts, from the surface water, river or lake, okay, and then groundwater. Some groundwater is stored underground, okay, and we withdraw them and use that in different parts of our society. Municipal here is domestic, so this is our home, okay. A part of it, we use that in our home. Some of them, we use that in the industry. So the things that you're wearing on your body, the clothes that you're using, people, the industries or the factories, they need to use a lot of water to produce just one shirt that you're wearing right now. Okay, so you think that you are not using a lot of water, that's wrong. Okay, every time when you buy something, you are already using the resources on the earth. Okay, and power plants, we talk about this, the thermal pollution, right? Also agriculture, of course, for the irrigation. And after we are done with the water, it's not gone, right? We have put something in the water. Maybe after you have taken a shower, then you release that back to the world, right? So the returns here is very important. So available for the next user, or we need to deal with this. We need to have water treatment for the returns. So in Japan, recently they have released the radioactive water, right? So what they call is not, it's not contaminated water. What they call is treated water. Okay, that's why, right? That's the concept of water quality control. Whether it's really treated or not, that's another issue. Okay, so water pollutants. So we have used the water and then dump the water back, right? So the return water will be polluted in some ways. So in the realms of environmental engineering, we need to study what kind of pollution that we will find, what kind of chemicals we'll find in the returns and deal with it. Okay, so different types of water returns, for example, agricultural, where do the pesticides go in the returns? Okay, and domestic, meaning this municipals, right? Domestic use. Of course, when we have taken a shower, the soap will go into the return, right? Or when you have taken medicine, sometimes you excrete that out of your bodies, right? It will also go back to the nature. Okay, and of course, human sewage. Okay, and power plants is thermal pollution, temperature elevated. So that's the pollution that we're talking about, thermal pollution. Okay, and industry, of course, a wide range of chemical pollutants. Okay, so there are different types. We need to define the different types. The first type, of course, is pathogens, which are the living part of the pollutants. Virus, bacteria, fungus, or other microorganisms. Why do we care about this? Because they are disease-causing organisms. Maybe it would destroy the ecology in the water body that you are dumping into, right? So also the next one is oxygen demanding waste. So the pathogens, they are already the oxygen demanding waste, and there are other types in here. For example, nitrogen, phosphorus. So the nutrients that you're dumping to the environment is going to be biodegradable. What does it mean by biodegradable? They will need oxygen for oxidation, okay? And the bacteria will decompose the waste in here, listed in here. So different types. If the concentration is very, very high, you are risking favoring some organisms over the other organisms. For example, if you are having too much nutrients in a water body, you will favor the algae here growing in your water body, which means that if this is excessive or extra growth, it's not supposed to be there, right? You are like a god to this water body, right? You're providing more nutrients to some organisms and they will use up all the oxygen. And that's not good for the ecology in this water body. Okay, so there are different nitrogen sources. So every time when you take in the protein, sometimes our bodies cannot store the protein, right? You will release the protein back to the nature. Then that's the nitrogen sources. So wastewater discharges, runoff from animal feedlots, chemical fertilizers, they all contain nitrogen. And also phosphorus sources. Phosphorus is coming from the fertilizers mostly, or domestic sewage. So these are the major problems, so we deal with them first, okay? So we have talked about this in our first lecture about the global nitrogen cycle. Nitrogen is supposed to be in our Earth system. So what we human beings are doing is that we are putting more in one place over other places. So which means that it's an unbalanced situation. We don't want that, right? So this is supposed to be giving you some idea. It's not the case that all nitrogen is bad. It's just that we don't want too much in one location. Okay, we also have the phosphorus cycle. So phosphorus is supposed to be in the Earth system. It's supposed to be circulating in the Earth system in different parts. Okay, in the ocean and in the solid part of the Earth, there's circulation. We just don't want too much phosphorus in one location. So this is a slide trying to show you that we do need phosphorus in our bodies, okay, because we need that for energy transactions. Okay, so there are also different other types of water pollutants. For example, salt. It is a pollutant, right? If we're talking about salt in our dietary, it's okay, right? Provided that if it's not too much. But if it's too much salt in our soil or in our irrigation, that's bad, right? And also heavy metals, it's causing adverse impacts on health. It's not very good for our health, okay? And it's accumulating in our bodies. And also thermal pollution and pesticides, we have already talked about this. Okay, so this is showing you why salinity or salt is not good sometimes, okay? So if you, before clear, so this is like a normal healthy situation where you have some forest and some groundwater here underground, and it's healthy. And here you are trying to chop down the trees and grow your cows here, right? It's a farm for the cows, okay? And if you're trying to do that, you will have irrigation because you need the grass, right, for the cows, okay? Irrigation, and then you will increase or raise this groundwater surface to another level, and you will end up having saline, is salty, okay, salty groundwater at the surface, and then that would further destroy your trees or forest in here, okay. Okay, so next we talk about how we can quantify the effect of the pollutants. We use biochemical oxygen demand. So before we talk about calculation, we need to first have some idea over decomposition. So whenever you dump some garbage or unwanted materials to the environment, it will contain some organic compounds, right? Carbon-based compounds. So the organic compound will require oxygen for decomposition inside the bodies of microorganisms. So I put the microorganisms here. It's like, so the microorganisms, they are digesting the organic matter, okay, here, with the help of oxygen, and turn that into simpler stuff in here, extract the energy in the organic matter, extract the chemical energy in the organic matter. So in turning that into carbon dioxide, water, and other things in here, that's called aerobic decomposition in the presence of oxygen, okay? Okay, what about the situation where you don't have oxygen? If you don't have oxygen, you will still have decomposition, but you will end up getting unstable products. So it's very common to see that in swarm gas, in landfill, okay? And the unstable products can be very unpleasant in the smell, okay? So these are the examples for the unstable products, okay? And of course, okay, you can see them in the landfills, because if you bury your garbage, there will be no oxygen, right, underground. So that's where the anaerobic decomposition happens, okay? And in this class, we try to stick to the aerobic decomposition as much as possible, because when you exhaust all the oxygen in any location, that's not good. Okay, we'll get to that. Okay, this is like a storytelling, a cartoon version of what we would observe in the environment. First of all, we have some pollutants, right? Nutrient load up, meaning that in the wastewater, we have excessive nutrients from different things, from the sewage, from the fertilizers, flush into this water body. And you are favoring some plants over the other plants. Maybe you're favoring, okay, you're favoring the plants over the fish, for example. Okay, so it caused the aquatic plant growth of algae. Okay, and there is algae blooms. Oxygen is depleted because the plants, you think that, okay, they're doing photosynthesis, but at the same time, they need to breathe too. So they use up all the oxygen, and the oxygen is depleted, no oxygen left. Okay, and that prevents the sunlight reaching other plants. So you are favoring these plants over the plants under the water body. The plants die. Okay, after a while, they die, right? So every living thing die after a while. The plants die and the oxygen in the water is depleted. So then when they die, they even further exhaust your oxygen because they are decomposed by the microorganisms and further using up the oxygen inside this water body. Okay. So decomposition further depletes oxygen, and then that's the death of the ecosystem. And we try to avoid this by doing environmental engineering. Okay, so how do we quantify this dissolved oxygen? It's just the concentration of O2 in water, right? Concentration of dissolved oxygen, DO, and we can use different type of units in here. So unit of mass over unit of volume of water. Okay, you have some water in here, and then you can count the mass of the oxygen. So the white dots here are supposed to be representing the dissolved oxygen. Okay, and I'm just repeating the units in here. I think I talked about this in lecture 2. Okay, so what's biochemical oxygen demand, BOD? So let's say if you have some organic matter, which is supposed to be the pollutant, right? It's inside the pollutant, and it needs some oxygen for decomposition. And the decomposition happens inside the bodies of the microorganism, as represented by this green oval in here. So different things. Oxygen are white dots, and the organic matter are the brown dots. And after that, okay, we might not care about these. We want to keep the thing aerobic. We want to keep everything aerobic, meaning that we want to keep this. We want to keep having oxygen. So we don't want to exhaust the oxygen in your water body. Okay, so first of all, you have some organic matter. And so the brown dots are done by you. And the white dots are, they were already present before you dump the organic matter. So the white dots, which means the oxygen is provided by the water body. Okay. Okay, and then your BOD serves as food for the bacteria. So BOD, what does it mean? It's talking about the brown dots in here. Okay, ignore this one, meaning that the organic matter serves as food for your bacteria. So they are eating the brown dots, but at the same time, it needs oxygen. Okay. So the bacteria utilize the oxygen when they consume the BOD, BOD meaning the brown dots. Okay, but BOD, what does it stand for? It stands for oxygen. So it's very confusing, right? Why would it say that it's consuming BOD? Because in here, this whole slide is trying to tell you that we want to guess the amount of organic matter, but we can't. So we use the amount of oxygen to represent the amount of organic matter. Okay, because every time when they digest the food, they need oxygen. You can count the number of oxygen inside and guess how much organic matter it is in the water body. So we believe that they are proportional to each other, these two. So the white dots are the thing we can measure, and the brown dots are the thing we are interested in. Okay, okay. So that's why we call the organic matter as biochemical oxygen demand, BOD. We are not actually interested in the oxygen. We are actually interested in the amount of organic matter. Okay. So we are turning the things that we want to measure into oxygen amount. Okay. So BOD is a measure of the impact of the organic matter in the waste, and high BOD, high impact, right? High BOD meaning that you need more oxygen. High BOD meaning high amount of organic matter. Okay, we have to be clear on this concept before we go further. Okay, so now what do? We want to put the organic matter inside the water body. And of course, your water body is providing oxygen, and then wait until, so that's what we want to do, right? We wait a few weeks until all the organic matter is digested by your bacteria. But it takes too long, right? It takes weeks. How do you do an experiment for weeks? Just one experiment, right? It takes too long. So environmental scientists or environmental engineers, we use the standard, which is BOD 5. We measure the oxygen demand after 5 days. We measure this one. It's called BOD 5 after 5 days. And we don't care what happened the rest of the story. For the rest of the story. Okay, and BOD 5 should be in the unit of concentration. So you're using the concentration of oxygen to estimate the amount of brown dots, which is the organic matter. Okay, it's representing the amount of organic matter. Okay, so you are using the bottom graph to study the graph here. You're using the BOD amount to guess the amount of organic matter. Okay. Okay, this is an example. So let's say if we need to oxidize one, so the bacteria, okay, the bacteria needs to oxidize one dot, brown dot in here. The bacteria will need 2 oxygen element, 2 oxygen unit to over 1 day. Okay, each day it will do this 1 time. And then next day 1 time, and next so on and so forth. Okay, so what does it mean? It means it needs 1, 2, 3, 4, 5 days to digest everything, right? And it needs 10 units of oxygen in this case. Okay, so this is the beginning. This is what we see in the wastewater. Okay. Okay, so unfortunately, sometimes your wastewater sample does not have enough oxygen. You can see that right here. If we still use the same example, right? Oxidize 1 organic matter, bacteria needs 2 oxygen unit. If this is the case, then this is not enough, right? We need 10 oxygen unit, right? We just have 1, 2, 3, 4, 5 of them. So what happened? If you leave that for 5 days, you will go into the anaerobic decomposition, and that's not good. That's not what we want, right? We want to use the amount of oxygen to measure the number of brown dots. If you don't have the enough oxygen amount, then you cannot do the measuring, right? So the oxygen demand of the wastewater is larger than the oxygen available, which is 5 in this case. You need 10. The demand is 10 and the available is 5. And you need dilution, meaning that you need to add the available oxygen to your waste sample in here. So how do we do that? We add some clean water, which is the dilution water in here. This is the dilution water. So originally, let's say if your waste sample is 100 milliliter and you add 200 milliliter, okay? And total, you will get 300 milliliter. And then you add a bunch more dissolved oxygen just because you add some dilution water, okay? And let's say if you have added 200 milligram, what did you do? You have added 10 units of oxygen because originally you have 5 in here. If they have the same ratio of dissolved oxygen, this 200 will give you 10, right? And total now you have 15. Okay? If you read the book, they will not give you they will not give you this cartoon version. They will give you some text, okay? Okay, so now you have the standard BOD bottle, which is 300 milliliter. Put them inside this bottle and wait for 5 days. Okay, and you need to calculate, you need to do the calculation with the dilution fraction. What is the dilution fraction? The volume of the wastewater, which is 100, and the volume of the dilution water for this one. The total, which is 300. So 100 over 300, 1 over 3. You have diluted that by 1 over 3. Okay. Okay. So now you have the two things in here, water sample and dilution water. Put that into your standard BOD bottle, 300 milliliter. So measure the concentration of dissolved oxygen initially. So at the beginning, you do measurement, which is the DOI in here, initial dissolved oxygen, and then wait for 5 days. During these 5 days, you cannot have sunlight shining over your standard BOD bottle because you don't want algae to grow. That will upset your dissolved oxygen measurement, right? No extra O2 supply. And keep the bottle sealed because if you don't keep it sealed, there would be oxygen in the air going into the water body. And also keep it at a fixed temperature. You don't want temperature to play a role in your experiment, okay? So, and then you measure the concentration of the dissolved oxygen, DOF, which is the final dissolved oxygen. You know that initial should be more than the final, so do the subtraction like this, okay? And the concentration, remember that it should be the unit of mass over the unit of volume, water. And then you have to divide this by your dilution fraction. We just calculated that is 1 over 3. Okay, so dilution, 1 over 3 in this case. Okay, now you have an example. So first of all, we start with 10 milliliter sample sewage. 10 milliliter, this one, 10 milliliter sample sewage mixed with enough water to fill with 300 milliliter bottle. So now you are filling up the BOD standard bottle with 300 milliliter. So meaning that your dilution water should be how much? 290 millimeter, right? 300 minus 10. You have to add 290 milliliter of dilution water. Together, they will fill up this bottle. It's a very small sample, 10 milliliter. Okay, so fill up the standard bottle. Has the initial dissolved oxygen 9.0 milligram per liter. So now you have the DOI, which is 9. Okay. To help assure the accurate test, it is desirable to have at least 2 milligram liter drop in the DO, in the dissolved oxygen. So you need the dissolved oxygen to drop at least 2, because if you do measurement, sometimes there will be uncertainties, right, for your equipment. And you don't want the measurement to be too small. If it's too small, then your uncertainty range, if it's too small, your uncertainty range is large enough, then you don't trust your measurement, right? So it should be larger than 2. during the 5-day run. And the final dissolved oxygen should be 2 again, so coincidence. So for what range the BOD5 would this dilution produce the desired results? So now you have like a range for your BOD5 because you want this to be larger than 2, right? To drop larger than 2. So your BOD5 is should be larger than 60 milligram per liter. Okay. And also they are giving you the initial and final dissolved oxygen level. And also they're giving you the dilution fraction in here. Okay, so it should be between 60, larger than 60, and smaller than 210 milligram per liter. Okay, so I forgot to mention one thing. So the question is saying that your final dissolved oxygen should be at least 2. What does it mean? It means that you don't want to exhaust all the dissolved oxygen in the water body. You want to have something left, right? So that you are making sure that this is aerobic. This is not anaerobic, right? So 2 is the minimum. At least 2, okay, minimum, yeah. If it's larger than 2, what happens to your BOD5? Larger than 2 is acceptable, right? So your BOD5 would be smaller. So that's why you're putting a smaller than or equal to, because it's an acceptable range. Anything smaller than this, acceptable range. Okay. So next we talk about a more complicated case. Sometimes your population of microorganisms is not big enough. It's not your fault, right? You have a lot of waste, you have a lot of organic material inside, but your microorganisms are too weak to carry out the biodegradation. So you want the biodegradation to happen in an aerobic situation. So next, how do we solve this problem? We add some microorganisms to the distilled water, a process called seeding. So if your microorganism is too weak, and then your organic matter decomposition is too weak, right? This curve is changing too slowly, okay? So what do? We collect the sample from the environment here. We collect the sample and it contains, what does it contain? What do we want to measure? We want to measure the organic matter inside this wastewater bottle, right? Inside this wastewater. And the bacteria is just a bonus, right? The bacteria, you are not interested in the bacteria. You're interested in the organic matter, but the bacteria is just too weak. What do? We add some bacteria in the waste sample. So now what do? We have, on the right-hand side, we have the waste sample. On the left-hand side, these are the things we want to add to your measurement. So we add dilution water to provide dissolved oxygen. And we also provide bacteria to kick off the whole biodegradation, right? Because the original bacteria is too weak. And then also we add some nutrients to facilitate the process. Okay, so in the first bottle, this is supposed to be like a control experiment, right? Seeded dilution water, seeded meaning adding microorganisms, dilution meaning adding dilution water and also nutrients. And we do the same to the second bottle, add these 3 things. And also we add the waste sample. This is the thing that we are interested in, right? Not the things that we have added, but we want to kick off the whole biodegradation, and we want to exclude the effect of the things that we have added. We want to exclude the effect of these 3 things. These are the things that we add, right? We are not interested in them. we're only interested in the wastewater. So we have like a control experiment on the left-hand side, so that when we do calculation, we can subtract that effect. And what do we have left? Just the wastewater, right? The effect of the wastewater. To put that in the mathematical expression is in here. Okay, so we have the oxygen for the mixture on the left-hand side, and it should be equal to the oxygen for the wastewater plus the oxygen for the dilution water. Oxygen demand, we're talking about the oxygen demand. Okay, and what are we interested in? We are interested in the oxygen demand for the wastewater only, right? So we have measurements from the mixture, which is the right-hand side bottle, and the measurement from the dilution water, which is the left-hand side bottle. Okay, and if we do subtraction, we'll find the oxygen demand for the wastewater. The first term on the right-hand side, we cannot find that from the measurement, but we can find this from the measurement. We can find the left-hand side from the measurement. Okay, so how do we put that in the mathematical expression? We do, we multiply the concentration with the volume, right? Because concentration is per unit volume. We just very, very simple multiply. For example, this is the BOD for the mixture, biochemical oxygen demand for the mixture, and then volume of the mixture. Okay, and here, this is the thing that we want to calculate. We don't have the value for this BOD for the wastewater. And volume of the wastewater, we do have that. It's 10, right? In the last example. Okay, and dilution water, of course, we can calculate, or we can find this from the measurement, right? Just wait for 5 days. And your BOD 5 for your dilution water will be this one. Okay, and the volume, you know that, right? You are the one who mixed everything here. So you know the volume for the dilution water, which is this one. Okay, BD. Okay. So this is just we express everything. Okay, left-hand side mixture. This one is the mixture. Right-hand side waste sample, VW in here. And the second term is the seeded dilution water, which means that we can have measurement for mixture and seeded dilution water and calculate the middle term in here. Okay. Okay, now we have the equation. We express everything in terms of the fraction of wastewater. So what's the fraction? It's very simple. Your volume of wastewater over the total volume of the mixture. Fraction of the mixture. Okay. So if we have this expression, we can rearrange the top equation in here, just mathematical rearrangement. And then finally, we will get the BOD of the wastewater, which is something we are interested in. So this one, we can find that out by measuring the BOD 5 for this. And for the dilution water, measure the BOD 5 for this one. Okay. And the P is just the ratio between the volume. It's a fraction. Okay. This is showing you how we rearrange the map. Okay. So here is, I know it looks very confusing, but everything here is just oxygen demand. Okay. So biochemical oxygen demand for the mixture, just do the subtraction, initial dissolved oxygen, final dissolved oxygen. And for the dilution water, again, initial dissolved oxygen, final dissolved oxygen. Same unit, everything has the same unit, which is weight per unit of volume, weight of the oxygen per unit volume. Okay, so if we arrange or we place the terms inside, you will have these two and these two, which is coming from the seeded dilution water. These two is coming from the mixture. Okay, here is an example. If we talk about a seeded BOD test, containing seeded dilution water is dissolved oxygen level dropped by 1 milligram per liter. So the seeded one, which is this one, seeded dilution water, BODD is 1 in the BOD5 test. So 300 milliliter bottle filled with 15 milliliter wastewater. So you know the dilution fraction, right? Just 15 over 300. The standard is 300. Okay. And the rest of the seeded, okay, it's not calculating that for you. It's just 300 minus 15, right? The volume of your seeded dilution water. Experiences a drop of 7.2 milligram per liter at the same period of time, meaning the mixture, right? The seeded water is the mixture. So you put 7.2 here. The drop is 7.2. The drop for the dilution water 1. And P is just the dilution fraction. So putting everything in here, we know that the BOD5 for just the wastewater is 125 milligram per liter. It's so much larger than the mixture and also than the dilution water, because it's just very small amount, right? It's 15 millimeter containing a lot of organic material. It's wastewater is supposed to have more organic material than your dilution water, right? Okay. Maybe we can take a break for 5 minutes first. Okay. Okay, let's continue. So next, we would study more about the biochemical oxygen demand. So assuming we have a closed system, which means that it doesn't interact with the environment. For example, the wastewater in a flask, the bacteria will oxidize the waste, right? That means that there is a change of the organic matter remaining over time, right? If your bacteria they keep eating your organic matter, right? The organic matter is the food. So we have a mathematical model. We have a model to predict what happened to the amount of organic matter. Okay, it should decrease over time, but how does it decrease? In what manner? Okay, so eventually all the organic matter will be gone, and we try to predict that with a model looking like this. So LT here is the BOD, or organic matter left. It's in the unit, again, it's in the unit of dissolved oxygen in here, but it's representing the amount of organic matter. I cannot stress this enough, okay? We have the unit for dissolved oxygen, but it's representing the amount of organic matter, the brown dots. So LT is talking about the white dots, but actually it's representing the amount of brown dots, okay? So the change of the amount of your organic matter, which is this line, it should be decreasing over time, right? It's because your bacteria, they are eating the organic matter. So the change of the BOD, or the organic matter amount, should be proportional to the dissolved oxygen, should be proportional to the amount of the organic matter itself. Meaning that if you have higher organic matter amount here, right? This is the axis for organic matter, right? If you have higher amount of organic matter, the change is larger or faster. The slope here is steeper, right? If you have small amount of dissolved, if you have small amount of organic matter right here, this is the region, right? We're talking about this region. Smaller amount of organic matter, slower change. The slope here is not steep, right? Steeper here, not steep in here. So we can express that in math by relating the speed of change with the concentration itself, the dissolved oxygen concentration itself. Again, this LT is representing the amount of the brown dots, organic matter. Okay, and we put a negative here because this is decreasing over time. Okay, and K is supposed to be a constant relating these two, the speed and the amount itself. BOD reaction constant, okay. And we can solve this differential equation, very, very simple differential equation. And if we solve this equation, we can have the expression for LT. It's in terms of L0, which is the initial BOD, meaning the initial amount of organic matter in here, okay? And it's decreasing over time. The time in the equation is in here, T. K is the reaction rate constant or reaction constant, BOD reaction constant, K, and you have the minus in here because it's telling you that it's exponentially decreasing. If there's no negative sign in here, it should be exponentially increasing. Okay, so what does it tell you? This equation, the solution. It tells you that the BOD left or the organic matter left is decreasing over time. Even though you are measuring the dissolved oxygen, you are telling yourself that I am measuring the organic matter. So organic matter decreasing. And the other part, the white part in this graph, is the dissolved oxygen used by digesting your organic matter. Okay, so if you add them together, they should equal to your initial amount L0. So L0 equals to your oxygen consumed, which is the white part, and the oxygen left behind, the organic matter left behind, organic matter consumed. Okay, which means that you can re-express this organic matter consumed, the white part, with the same equation in here, with the equation above. We express this BODT. So both of them are BOD. Both of them, all of them, actually, all of them, they have the same unit, which is milligram per liter. It's talking about oxygen amount, right? But they are representing different things. Okay, L0 is the total or the original initial organic matter amount, L0. And this one is O2 consumed, which is the white part. And this one is the O2 left, which is the pink part. Okay. Okay, so if we want to look at this example, okay, estimating the L0 from BOD5, how do we do that? L0 meaning this one from BOD5. So you are looking at the value at this time, right? X-axis is the time, right? 5 days. So you are pinpointing this point. You want to find, you have this one, BOD5. You want to find L0. How do we find that? So the dilution factor P for the unseeded. So remember that you're not using the seeded equation. For the equation sheet that I provide to you for the exam, it will not tell you if the equation is seeded or unseeded. So you will have to remember that. Okay. Unseeded mixture, we will use this equation. Okay. Of waste and water. So they are giving you the P value, not the statistic P value, the fraction. Okay. The fraction here is 0.03. So substitute that into the equation. And the DO, dissolved oxygen of the mixture, is initially 9. So putting that into your equation. After 5 days, it dropped to 3. So very simple calculation in here. BOD5 is going to be 200. So this one is 200. BOD5, 200. Okay, what about the rest of it? If you can calculate this L5, then you can calculate L0, right? Just add them together. Okay, what is L0? We have BOD5, right? So use this equation. Use the second equation in here. So we want to calculate L0. BOD5 is 200. And you know the reaction rate constant K is given to you, 0.22. It's per day, but you don't have to turn that back to standard unit because you are multiplying by number of days in your equation. So if you multiply them, the unit would be gone, okay? And L0, you know that is 300. This should be L. Okay, now you can find L at L0. They're asking you, what is the 5-day BOD of the waste? So it's 200. What would be the ultimate carbonaceous BOD? So the ultimate carbonaceous BOD is this one, L0. Ultimate meaning that is the maximum amount. Okay, maximum carbonaceous. Carbonaceous meaning we're talking about the organic matter, the carbon inside. So how much oxygen we need to digest all the carbonaceous material in the organic matter. So it's asking you the L0 for B. Okay, and what would be the remaining oxygen demand after 5 days? So now we find L0, so we can just do simple subtraction. 300 minus 200, that would be 100, right? 100 milligram per liter. Okay, so it turns out that this K is not a constant. The so-called BOD reaction rate constant K is a constant, or is a parameter telling you that how fast is the biodegradation happening, okay, of the waste. Okay, if it's larger, then it's faster, right? Smaller, then slower. Okay, and it depends on different things. What does it mean by depending on? It means that it can change, okay? And it depends on the nature of the waste itself. So different pollutants will have different reaction rate constant. So probably if you go take a sample and do measurement, you're trying to estimate this K first. Okay, pinpoint the K, and then you can do different calculations. And also it depends on the ability of the microorganisms. So two things, the nutrients and the microorganisms. So it may take some time for healthy population organisms to be able to thrive. So this is talking about logistic growth, but we're not talk about that here. Okay, so also it depends on temperature, of course, right? If you have higher temperature, then the reaction rate constant should be higher. So now we have the adjustment of the reaction rate constant. So what you are given in the question, most of the times the K only applies for 20 degrees Celsius. It's like the standard ambient temperature, environmental temperature. Okay, but what if you have higher temperature? You have to recalculate the reaction rate constant with this empirical equation in here. K20 is the reaction rate constant at 20 degrees Celsius. You readjust this with the term in here. Theta is experimentally or determined in the laboratory. Okay, theta here is not temperature. Okay. So in the last example, we have the BOD equal to 300 milligram, the ultimate BOD, meaning L0, 300 milligram per liter, the concentration of BOD of dissolved oxygen. And at 20 degrees Celsius, the 5-day BOD was 200, this one, okay. So you have to be very clear about different terms in here in your exam. You will get confused if you don't remember, okay, because they all talk about dissolved oxygen level. Okay, and the reaction rate constant was 0.22 per day. So what would be the 5-day BOD of this waste be at 25 degrees Celsius? Now you have to readjust this 0.22. How do we do that? Substitute that into the equation here, 0.22, and this one is given 1.047, and then we minus the degree, right? 25 degrees Celsius at your current case, and you will have a higher reaction rate constant. Originally it's 0.22, now it's 0.277. Okay, So we calculate everything in here. Calculate the BOD5 again with the new reaction rate constant. So this is not a variable called K5. This is K multiplied with 5, okay? So if the ultimate O2 amount, which is L0, is the same, you will end up having this decreasing faster and faster, because now it's not 200 milligram per liter anymore, it's 225, meaning that after 5 days, you have used 225 milligram per liter instead of 200, because the temperature is adjusted, okay? Meaning that you will use up your dissolved oxygen faster in a higher temperature environment. Okay, so this is a summary for what we had discussed. Okay, on the top, we talk about the ultimate carbonaceous oxygen demand L0. Okay, and we can use this to simulate the organic matter left in your water body by this equation. And if you flip that around and look at the change of BODT, the amount of oxygen used or the amount of organic matter digested, okay, we can use this equation. It's just flipping around, right? The top equation in here. Okay, if you flip this equation, it would be looking like this. Okay, it's just flipping, right? Upside down, flipping the curve on the top upside down. So the used one is on the bottom. The equation is in here. So the same equation with this one. And we can add the two terms to become L0. L0 is like the total ultimate oxygen needed plus the consumed and the left behind. Okay, so next we talk about other things. I think we have talked about the nitrogenous waste. So we all the living organisms, we need protein. We do protein synthesis in our bodies. So different living organisms, and inevitably we need to excrete that because we cannot store the nitrogen in our bodies. We can use them, but we cannot store them. If we cannot store them, we have to excrete, right? We have to release that. So they have different forms in different types of organism. For example, birds is a more complicated chemical component, and in mammals or fish, we release them with ammonia. Okay, that's what we find in the wastewater, because everyone goes to the restroom, right? So why do we talk about nitrogenous waste? Because if you release that to the environment, it's going to need oxygen to decompose. Okay, which means that we might need to talk about the oxygen demand coming from the nitrogen we release to the environment, which is ammonia in here. Okay, so it can be turned into other things with inside the bodies of this kind of nitrite bacteria. I don't know how to pronounce this. Okay, so after it had turned into the nitrite, NO2 minus in here, the NO2 minus will be turned into other things. The nitrates in here. Okay, and further using up the oxygen in your water body. Okay, so the oxygen used in the nitrification in here reduces the water quality. Okay, because it use up the oxygen. So the last part, we talk about the organic matter decomposition, right? So it's called carbonaceous oxygen demand. And for this slide, we talk about the nitrogenous oxygen demand. So both of them will need oxygen to decompose. Okay. So organic nitrogen will be turned into ammonia and then turned into nitrite and then nitrate. Okay, and because we have different species of nitrogen, we might need to talk about the change over time. So at first, there is conversion from ammonia to at first, there should be organic matter, right? Turning into ammonia. Okay, so that's why it's increasing over time, your organic matter decreasing. And then after a while, the ammonia is turned into nitrite. So you can see this. And then after a while, it's turning into nitrate. So you can see this. Okay. And all the processes here, it will need oxygen. So if we also encounter for the nitrogenous oxygen demand, after a while, after 5 days, maybe, it may be more, we will also see the effect of nitrogenous oxygen demand. So that's why sometimes we would do this so that we won't have to deal with both of them. Okay, so this question is asking you the nitrogenous oxygen demand. Okay, so now we have some domestic wastewater of 30 milligram of liter of nitrogen. So we're giving you the concentration of nitrogen in the form of either organic nitrogen or ammonia. Assuming that very few new cells, so assuming that the nitrogen is not used for the bacteria to build new tissues, okay, and assuming that they use them up, they decompose them up, okay. Assuming this is the case, find the ultimate nitrogenous oxygen demand for this wastewater, for this wastewater containing this amount of nitrogen. Okay, so now we combine the two chemical equations. Combine them, so this is the new one. It's easier to deal with. So now remember what we have learned in the environmental chemistry lesson. So 1 mole of nitrogen here will need 2 moles of oxygen to do the decomposition. Okay, and the question is giving you the concentration of nitrogen, which is this one, nitrogen here. I've highlighted that in red. We want to calculate the oxygen demand. Okay, so how do we do that? It's very simple. So 14 over 30 milligram of liter given by your question, and 64 is actually the molecular weight of your oxygen here. 32 gram per mole of O2, and minus 2 would be 64. So 14 gram of nitrogen needs 64 gram of O2 for the decomposition. So if you don't remember how to calculate this, please refer to this one, 16 times 4, 2 and 2 here. Okay, it's 64 gram. So now the ultimate nitrogenous BOD would be 137 milligram. Okay, so there's a part B for this question. The ratio of the ultimate nitrogenous BOD to the concentration of nitrogen in the wastewater. So just very simple. So it's ratio, right? 137 from the last question, 30 milligram per liter of nitrogen, which means that per unit of nitrogen, you will need 4.57 milligram, 4.57 unit of oxygen. Okay, so next is oxygen demand based on rivers. Okay, so this is a special case because river is a flowing structure, right? So we need to calculate the flow rate. So the ultimate BOD for the mixture, what is the mixture? The mixture is talking about, let's say if you have a sewage outflow in here and you have a river and they would mix together at this point, right? This is the mixture. I have highlighted that here with a dashed line, okay? And we can go back to use the equation that we have here. In the past, we have used, what did we use? We used the volume flow rate times the concentration of something, right? Volume flow rate times the concentration of something. Okay, this is a revision for you. Volume flow rate, which is Q, times the concentration, which is mass per unit volume. So the concentration here is talking about oxygen concentration. Flow rate here meaning that you have some flow, right, across your river. Okay, if you multiply them, that would be your mass flow rate. Okay, mass here, kg. Okay, so this is like a revision for you. We had talked about this in lecture 2. So mixture here. So the main character in this story is the pollutant, right? In the lecture 2. So for our river, the main character in this story is the dissolved oxygen. Remember that, not the pollutant anymore, because we care about the water quality, which is defined by the dissolved oxygen. Okay. So how do we do that? It's very simple. So this is an example. Maybe example would be more easy. It would be easier to study problem. Okay, so now we have a wastewater treatment plant serving around 200,000 people. And these 200,000 people discharge this much of water, 1.1 cubic meter per second. And having the ultimate BOD, so you know the L0, right? Ultimate BOD is L0, 50 milligram per liter. So per 1 liter of the wastewater, you will need 50 milligram of dissolved oxygen to digest everything. Okay, so we release this into a stream that has a flow. So you have volume flow rate and the biochemical oxygen demand of its own. So this, it turns out that in the inside the stream here, it also have some organic matter, right? Of course, in the wastewater, you have a lot of organic matter. You have a higher BOD, but in the stream itself, naturally, it also contains some organic matter, right? Naturally. For example, if it's autumn, then you have a lot of tree leaves, right? That's organic matter. Okay. So it has its own BOD, 6.0 milligram per liter, much lower than the polluted sewage here. Still, you have some value. Okay, and the deoxygenation constant, KD, we'll get to this part later, maybe for the first part, for part A first. Assuming complete and instantaneous mixing, so very thorough mixing in here, estimate the ultimate BOD of the river just downstream from the L4. So at this location, right at the location of the mixture, what is the L0? Okay, what is the ultimate biochemical oxygen demand? So it's just the same as calculate any type of concentration with this equation. So we have wastewater, we have the river, and we have the mixture, right? So the mixture is L0 times the total volume flow rate. If you put that back over to the left-hand side, right? The mixture on the left-hand side. Okay, and the total volume flow rate should be the volume flow rate from the stream and also from the stream and from the sewage. So add them together from the river and from the wastewater. Okay, and you can put everything back. So for the wastewater, the volume flow rate is 1.1 given by the question, and 50 biochemical oxygen demand. Yeah, this one, ultimate biochemical oxygen demand. You cannot just add 50 to 6 because they don't have the same volume flow rate, right? And here, for the river, is 8.7 cubic meter per second volume flow rate of the river, and then biochemical oxygen demand for your river. Okay, and finally, you will get the combined biochemical oxygen demand, which is 10.9 milligram per liter. Starting from here, your ultimate biochemical oxygen demand is 10.9, which means that L0 can be used for the following calculations. It will decrease over time, right? It will start the digestion along the time and along the distance, but at this location is 10.9. Okay, so now we care about the downstream. Let's say if we have the mixture at this location, the same question again. So part B, The next question is asking you if the stream has a constant cross-section, meaning if you go along, it will not become bigger or smaller, just the same cross-section. So this picture is not accurate in here. Okay, so that it flows at a fixed speed equal to 0.33 meter per second. So it's giving you the flow rate here, right? So estimate the BOD, the speed of the river. Estimate the BOD remaining in the stream at a distance 30 kilometers in here. So how do we turn that into time? So just speed equals to distance over time, then we can turn that back to time, right? Because the x-axis here is time. We only have the change over time. We don't have the change over distance. So very, very simple. Distance 30 kilometers, speed 0.3 meter per second, turn that back to time. What is the time? The time is here, right? 30 kilometers divided by the speed. And we turn that back to the number of days because the reaction rate constant is per day. So you might have to change the unit of your time to day. Okay, 1.16 day. So your river travel 30 kilometers in 1.16 day. That's the meaning for this. Okay. Okay, then after that, we calculate the BOD remaining. So which one is remaining? LT, all right, LT is remaining. BODT is used, is the used part. So LT substitute the initial biochemical oxygen demand, the ultimate carbonaceous biochemical oxygen demand, L0. You got that from part A of this question, okay? And KD is given to you, reaction rate constant 0.2 per day, and after 1.16 day, the oxygen left behind is 8.7 milligram per liter. Okay. Okay, so we need a certain amount of dissolved oxygen in river, and there are different sources of dissolved oxygen, and there are different removal mechanisms. So how do we account for all of them? So there are different sources and different things. The sources would be, first of all, of course, the oxygen from the atmosphere. They would be mixed into the water body by wind, waves, and current. Of course, there's diffusion, okay? And also input of O2 by photosynthesis of your sea plants or phytoplankton here. And also removal, we had just talked about this, right? Removal of oxygen by the decay of organic matter or decomposition of the organic matter, okay? And we don't want this dissolved oxygen to be too low, okay? If we talk about the unit of milligram per liter, if it becomes 1, only worms can live, okay? All the fish will die, okay? To have a healthy ecosystem, we should keep it at least 5 to 6, right? Milligram per liter. Okay, so next we need to talk about the deoxygenation, the removal of oxygen by any processes. So in the last part, we talk about the digestion of organic matter, but here we don't care about which process. We just care about the speed of deoxygenation. Okay, so the rate of the deoxygenation equals to the deoxygenation rate constant times the LT. LT is here, this one, not L0. Okay, LT. So at any time, the decrease of oxygen will be depending on the oxygen left behind, which is LT. Okay. So here we can rewrite the rates of deoxygenation by rewriting LT because we have the equation for LT in the last part. If we rewrite this LT, this is talking about the change of LT due to carbonaceous oxygen demand. okay, and that contributes to a part of the decrease of oxygen, which is studied by this, okay. Okay, next time we'll talk about this. It's a little bit confusing, so I'll leave that to the next week, because this one, the oxygenation, is talking about the properties of the river only, okay? So this lesson, we talk about the effect of the organic matter, and next lesson, we'll talk about the properties of the water bodies. So this is talking about the properties of the water bodies, not we are leaving the region for organic matter. Okay, next time maybe. Okay, any questions? Okay, if not, next time we'll do the tutorial.